Welcome, General Chemistry Nation. We're now getting into electronic configurations. And periodic trends. So that's the topic of Module 3. So just as just a quick review, because we're really tied into the last module, is that we have 4 quantum numbers that basically provide a model for us to understand how the electrons are, hanging around the nucleus when electrons are all negatively charged and are repelling one another. This is like basically 2 negative ends of a magnet. The quantum numbers allow us to understand that the electrons are separate from one another. Right, due to energy. Right, that would be n, our principal quantum number. Orbit, which would be our angular momentum quantum number. Housing unit, which we could say is the magnetic quantum number. And spin. So that's really what the 4 quantum numbers are allowing us to do, is to be able to just get a model together to split these electrons up so they're not all in the same region. They're actually in different regions. They're in different energetic regions. They're in different orbits. They'd have different magnetic properties within those orbits or housing units, as well as this idea of spin. So that's where we left off, is this idea of the 4 quantum numbers, and I know that's a bit much with the principal levels of n and then the sub-levels as we go down from that. So we'll keep reinforcing these ideas in this lecture as well. So the first topic is electronic configurations. Right, and this is 4 elements. And this basically just describes, how, or where the electrons reside about the nucleus. So before we get, into describing all these configurations, we do have to have a couple rule sets. And the first rule set is the Pauli exclusion principle. And the Pauli exclusion principle says that no two electrons can have the same 4 quantum numbers. And we talked about that in terms of N, L, M sub L, and M sub S, where we have our principal, we have our angular, we have our magnetic, and we have our spin. So those are the 4 quantum numbers. And remember I was saying that they describe it's almost like a map, right? Or a location. I guess you could say it's an address, right? Just like you have an address with your house number, your street, your town, your state, your zip code, right? These could all be maybe envisioned as quantum numbers, meaning that, with all of those pieces of information, I know where you live. If I have all these pieces of information with these quantum numbers, I know where the electron lives or where the electron resides. So that's the idea with these 4 quantum numbers. So we can't have basically 2 electrons having the exact same 4 of them. So for instance, let's look at the element helium. And helium has 2 electrons in the 1s orbital. So if we look at helium, helium has that atomic number of 2, right? It has that atomic mass of 4. And so that's where the 2 electrons are coming from those 2 protons. And if I were to draw an orbital here indicating the 1s, I would have basically 2 electrons within that 1s orbital. And if we were to look at each one of these, we find that they have different quantum numbers. That what is n? Well, I'm in the first level. What is L? Well, I'm in the s orbital. So that's an L of 0. Since L is 0, that means M sub L is also 0 because there's only one of the s orbitals per principal quantum level. And then my spin is plus 1/2. So those are the 4 quantum numbers that describes the first electron. And for the second electron, we would find that the numbers are pretty much the same, that we're still in the first principal level, we're still in the s orbital. There's only one of those s orbitals, so our M sub L is equal to 0, but now we have a minus 1/2 because it's pointing down as far as the electron. And this is what this is saying, that no 2 electrons have the same 4 quantum numbers. So that's the logic with the Pauli exclusion principle, is that when we are putting electrons into these housing units, if you will, we have to be careful in the fact that we can only basically fit 2 per orbital, and one has to be pointing up and one has to be pointing down. So that's really the take-home message. So that's the logic of the Pauli exclusion principle. It's saying that we have orbitals. We've talked about some of those orbitals like S, P, D, and F. We talked about principal energy levels where they can fall, like 1s or 3s or 4s. But when we're putting electrons into these orbitals, we can only put 2 max. And we must have this opposite spin as to not disobey the Pauli exclusion principle that, if they were both pointing up, well, then all 4 numbers would be exactly the same. So when we're putting electrons into these orbitals, we find that there is this ability for each orbital to hold 2 electrons. One of them would have a spin up, and the other would have a spin down. That takes us to then the off-ball principle. And the off-ball principle says that, when we're filling in electrons into these orbits or orbitals, we start from the lowest energy first and then move up. As those lower energies fill. The periodic table is a great guide to this idea. So that's how I would actually kind of really look at the off-ball principle in terms of energetics, is really starting now to kind of understand the periodic table and what other information we can get from the periodic table. We can get, the elemental symbol. We've talked about now numbers of protons, number of electrons, number of neutrons, as far as our atomic number and our atomic mass are concerned. But what we're going to realize as we go throughout this course is there's actually a lot of other information that's part of the periodic table and how it was actually developed. So getting to understand how the periodic table is a really good tool for us, much like our calculator is a good tool. Our periodic table is also a fantastic tool in helping us to understand elements. In this case, their electronic configurations and energetics, but also then going forward as we go through this module in terms of periodic trends, chemistry, why elements do what they do. So let's look at the periodic table and start to put together the ordering that we have of these electronic orbitals going from one level to the next. So here we have our periodic table. Just making it a little bit bigger. And one thing we have to understand is that N is really looking at these rows that we have going from the top hydrogen down to the bottom francium. So that's giving us a sense of our levels as far as our principal quantum levels that we tend to be in. Well, there's a little bit of play here with these, but that's what we see for a good chunk of the periodic table is this type of stratification. So if we start with our hydrogen atom, right, and that's kind of our initial, we have to remember that, as we go from one element to another, in the sense of left to right, we are adding a proton, right, because we're changing the element, but also we are adding an electron, because elements on the periodic table have the same number of protons and electrons, right? Because they're neutral. So we just have to realize that process as we go from left to right, that we're changing from one element to another, meaning that we're adding one proton and then another proton, but we're also adding one electron and then another electron. So let's get a better picture of that. Let's bring that periodic table back. And look at the flow that we have. Again, we have this idea of N in terms of our 1, 2, 3, 4, etc. And we're starting with the hydrogen atom, and we're going left to right. So the hydrogen atom has one electron. It is in the 1s orbital. As we then go to helium, helium has 2 electrons, and that's also in the first level. So we would have then, once we're full, 2 electrons in the 1s orbital. And so now we have what's, basically full on the other side. As far as this denotion, we have here N is equal to 1 as far as our first level. We have S, which is our L equal to 0, or our s orbital. And then we have 2 electrons in the actual orbital that is there. So that's how we actually fill in these as we go in terms of our electronic configuration. So we have our first number, which is our n level. We have a letter, which is representing our orbital that we're actually in. And then we have a superscript number here, which is representing then our number of electrons that are actually in that orbital. And so we're full up to the 1s2 once we get to helium. We then go down to lithium. And when we get to lithium, notice that now we're in the second level. And to begin, we start with our 2s orbital. And we can put 2 electrons into that 2s orbital. And that basically takes us to beryllium. Beryllium has 4 electrons. 2 of those electrons are in the 1s. 2 electrons are in the 2s. And then as we keep going to the right, we end up with boron. And now we're in the 2p. Right, first we have s orbitals, then we have p orbitals, then d, and then f. But realize that we have those quantum mechanical rules that only certain sublevels can be present within each quantum level or principal quantum level. So in the first level, all you can have is S. In the second level, actually all you can have is S and P. And remember, there are 3 orbitals in the P set. And since with our Pauli exclusion principle, each orbital can house 2 electrons, we actually get 6 electrons in that 2p. And just as kind of a side note here, if you count up the total number of electrons, we have a total of 8 electrons, or 8 elements in, going, left to right. So if we count up from lithium to neon, we have 1, 2, there is our 2s, and then we have 1, 2, 3, 4, 5, 6, and right there is our 2p. So just like with hydrogen going to helium, we have, the 1s full and going from 1s1 to 1s2. Right now we actually have more. We have now the 2s2 and the 2p6 are actually full. And then we go down to the next level, looking at sodium and magnesium. So you can see that the periodic table is split up in such a way to think about these orbitals and how many electrons these orbitals can actually house, and going from left to right. Neon has a total of 10 electrons, right? We know that because neon's atomic number is 10. So it has 10 protons. It must also have 10 electrons in that neutral state. Where are those 10 electrons? Well, 2 of them would be in the 1s2, 2 would be in the 2s2, and 6 would be in the 2p6. And that gives you a total of 10 electrons. So it's really describing where these electrons are being housed from one element to another. So if we go down to the third level, we're looking at sodium. Now we have our 3s2, right? And that's filling in what we have here. There's our 3s. And now we're going to our 3p6, and we're filling that up. And so now we're off to the right with aluminum all the way to argon, and there is our 3p. So when we get to argon, we now have the 3s2 and the 3p6 as being full. All right, so that's the beginning, and somewhat simplistic in the sense that we're only talking about two different orbitals, s orbitals and p orbitals. Obviously, we have different principal quantum levels, but still just those two sets. So if we keep going, the next level would be the 4s2, where now we are filling in this set of orbitals with potassium and calcium there, those outermost electrons in the 4s. And then we have this big block of elements here from scandium all the way over to zinc. Now, if we count up the number of slots, we'll find that there are actually 10 of them. And so this is where the D set now comes into play. We've talked about S and P. Now we need the D set to come. Now, the problem that we find is the numbering. So here we have our 3D10, and you notice we went from 3p6 to 4s2 to 3d10. And so what we have to understand is, the first time you have a d orbital is in the n is equal to 3 level. So that's why we must have the 3D at this point. This is definitely a problem with students because, we're in that fourth row. We see the pink 4 over there. We filled in the 4S already. Why isn't this the 4D? Well, the reason why it is not the 4D is because, again, the first time we see a D set is with our n is equal to 3 principal quantum level, right? And that just has to do with the rules for these, layers of L. The first time we see an S is in the first. The first time we see a P is in the second. The first time we see a D is in the third. And eventually we'll figure out the first time we see an F is in the fourth. So we have to keep that in mind. But if you look at the number of slots that are there, it does coordinate to this D set with 5 orbitals, each orbital housing 2 electrons. And so that's where the 10 electrons or the 10 spots come from. And then we're filling in the rest of the P block with our 3p6. So here we would have now 4s2, 3d10, 4p6, and so now that's all the way over and full. We now find kind of a repeat of that scenario. Now we're down to level 5. We're looking at rubidium and strontium. And so here we're filling out the 4s. Sorry, I apologize. I should have wrote that, 3D up there. Things are getting kind of crowded. We then have our, that's the color I picked, our 4D. And that doesn't look good, but we'll just have to kind of remember that. And now we have our 4p. So here again we see now we have the 5s2, the 4d10, and the 5p6 that is full. And so we're writing that out here with this energy diagram as far as how we're putting in these electrons in orbits. So now we have to kind of keep going, and here is where we now find another somewhat of a hiccup within the system. We are going to come now to this area with our cesium and our barium. And so that's when we would be filling in, now coming down below here, the 6s2. Right, so there's our 6s. Looks like I made a mistake above. I apologize, shouldn't be 4s there. That should be a 5s. Apologize for that. And now what's happening here is this area, this lanthanum area, which is actually pointing us down to here. If we count up the numbers, cesium is 55, barium is 56, and then if we keep going, we have ruthenium 71, if we're going from left to right. So there's a whole slew of elements that are missing, and that's the lanthanide series below. So we go from cesium 55 to barium 56 to then lanthanum 57, and then we're going through cerium, etc., across all the way over to yttrium number 70. And then we're coming back. Meaning once we're done here, now we come back up, and then we continue to fill our D set. So that we have here is the 4F. So that's where the F block is. If we count up the number of slots, you'll find there are 14 of them. The F set has 7 orbitals, each with 2 electrons. That would be 14 electrons or 14 slots like we see here. So in going from the 6s2, we then actually jump down to the 4f and fill that up. And then we jump back to the D set. And in this case, we're in the 5D set. And then we can go over and fill up the 6p. So with that, we have our 6s2, 4f14, 5d10, 6p6, and now that is full. So as you can see, complicated once we get much further down. But again, it's still organized by these number of orbitals within the sets, within S or P or D or F sets, in terms of the periodic table and how it's put together. That brings us down to the final level for us, at any rate. And so now we're looking at the 7s. So we're looking at francium and radium. So there's our 7s. We then find again, we have this idea of coming down now to the actinide series. So we're then also filling in the 5f that we see here. So we would start with our 7s2 and then our 5f14. And now we're going down the line. with our D set. This particular periodic table doesn't have all of them named out. We're actually filled out currently with the periodic table all the way out to the noble gases area. Just an older version here that we see with the periodic table. But that's where we go back to. So just like with the 4F, we went back we do the same thing with our 5F. We come back to there just like we did the same thing with our 4F, but we were going further up to the ruthenium. And then we can fill out the rest of the bunch there as far as that goes. So I'm just going to make that arrow a little bit better. So that means we then went from the 5F up to the 6D, and then we're filling out the 7P6. And we are done then with that scenario. So at the very top here, we then have finally the 7S2, the 5F14, the 6D10, and the 7P6, and now we're full there. So that is the ordering that we have of electronic orbitals. We have to start at the lowest energy first, the first level, and then we fill in electrons as we go, moving up in orbitals as they are filled. So we go from the 1s, and then when that's filled, then we go up to the 2s. When that's filled, up to the 2p. When that's filled, up to the 3s, etc., etc., etc. So the last rule that we have to know would be Hund's rule. And Hund's rule states that in filling of degenerate orbitals, one electron goes into each degenerate orbital before pairing occurs. So if we look at an example of this, we could look at carbon. Carbon has, an atomic number of 6. And if we bring in a periodic table here, a smaller one, just to give a sense of where we're looking, right, we're right here with our carbon atom. So if we look at the energetics of as far as an electronic or electronic configuration, right, we would have to say that carbon has 6 electrons. We could start with the 1s. We then have the 2s, and then we have our 2p. So those are the orbitals that we would house the electrons for carbon. And our electronic configuration would then look like this. One s2, 2s2, 2p2. There's also this idea of an orbital diagram. And this basically shows the housing units with also a relationship of energy. So there are really kind of two ways that we do these orbital diagrams. One would look like this, where we have energy increasing up. The other is where it's more of a horizontal idea and energy is increasing from left to right. And so we would write first our 1s, then we have our 2s, and then we have our 2p. Right? Those are the levels that we have, and maybe it'd be better to put those just on the side. And then the other way to write that would be 1s, 2s, 2p in this framework. So they're both really kind of saying the same thing. It's just, whether it's vertical representation or horizontal representation. And so if I'm looking at carbon, right, with those 6 electrons, I would be placing them in one at a time. So I first start with the 1s. I put 1 in there, and then I pair it up. The 1s is full. Now I go to the second level. I put 1 electron in, and then I put my next one in. Now the 2s is full. So now I've dealt with 4 of the electrons that carbon has. Remember, it has 6. And now I'm putting them up into the 2p. And according to Hund's rule, remember, I want to do it so that they are separate from one another, right? Because I want to put in 1 electron into each before I start to pair up electrons. So in both cases, we end up with something that looks similar with that notion. So degenerate orbitals are orbitals of the same energy. So, for instance, the P or D or F are multiple sets of orbitals that are all within a particular scenario. So above here, the 2p is a degenerate set of orbitals. They're all at the same energy. So that's why we have to put them in one at a time. So since they're the same energy, we can't differentiate putting it in filling up one level or filling up one orbital without first putting them all in separate. The reason behind that is once you have the pairing occurring, such as we see in the 1s or 2s, there's actually a lowering of energy. So if we were to pair up those 2 electrons in the 2p, well, it essentially wouldn't be fair to the others. I guess you could think of it that way. But since they're all the same energy, that's why, according to the off-ball principle, and now with Hund's rule, we have to put them in one at a time before we start to actually start to pair. So with that idea of looking at carbon with that notion of 6 electrons, where we can draw the same, kind of schematic that we had above with the 1s, the 2s, the 2p, whether that be vertical or horizontal, and do something like this, right? This is incorrect. Right? This is a violation of Hund's rule. Put in singular first, then pair for degenerate orbitals. So that's the incorrect version, and then as we see above, right, that's the way we would want to do it there, as far as, not pairing yet until the 2p is, half full. So this is incorrect. Let's do another example of this idea. So we want to write the electronic configuration and orbital diagram for sulfur. So if we look at sulfur, sulfur has roughly a mass of 32 and has an atomic number of 16. Let's bring up our roadmap here. And we are looking at sulfur, which is right there. So that means in filling up our orbitals, right, we have all these electrons for sulfur. It has, the 1s with those electrons. We continue down, the path, right? We have our 2s and our 2p. And then going one step further, we have our 3s and then our 3p, which is then going to stop right at that sulfur atom. So if we are to draw its its electronic configuration, that would be 1s2, 2s2, 2p6, 3s2, 3p4. So that is the electronic configuration for sulfur. If we were to do an orbital diagram, right, again, we would have now those levels written with terms of energetics. Where we would have our 3p, our 3s, our 2p, we have our energy increasing in a vertical nature. You know, or if we want, that's the last time I'll do the both representations. Where we have our energy left to right. So in terms of our element, right, we're talking about sulfur. And we have 16 electrons that we need to deal with. So plugging them, then we start at the bottom, first pairing up the 1s, then we fill up the 2s. Now we go to the 2p, and I just kind of have a habit of this. Like at first what I do is I always invoke Hund's rule. 1, 2, 3. Okay, now there's 1 in each one of those degenerate orbitals. And now I go back and I start to pair. So there's our 2p, which is full. And then I have my 3s with those 2 electrons. And now I have 4 electrons to put into the p. And so I do it 1 at a time and end up with this particular orbital diagram. Or if we did it on the other side, we would see something very similar. Sorry, it's a little bit more crowded over here. And so we end up with something that looks like this. If we had the 3p like this, this is incorrect. And that goes back to Hund's rule. So there's another example of writing an orbital diagram as well as an electronic configuration. So it does become a bit of a pain, though, I'll be honest, right? Especially when you get to elements further down on the periodic table, because you're writing this again and again and again. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, again and again and again. So there is a shorthand way of kind of getting around that. And since, remember, these noble gases or this noble gas spot on the periodic table houses full shells of electrons, we can use them as a representation of electrons, or electron orbital sets that are already full. So, for example, let's look at bromine. Bromine has that atomic number of 35, and we want to know, the electronic configuration. So if we look at our periodic table, we are down here now with the bromine. So that means we have a lot of orbitals to talk about, right? We have the 1s that's full. We have our 2s and our 2p full. We then have our 3s and our 3p full. And now we're down into the 4s, the 3d, and now our 4p up to the bromine. So if we were to then, address that electronic configuration, right, we have quite a bit there as far as, I'm just going to bring it down actually to have space with it. We'd have a 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p5. So there would be our electronic configuration for the bromine atom. But if we consider this whole block, right? This whole block is really equal to argon. Right? If we calculate how many electrons that we have here, right? We have a total of 18 electrons. Right? And that's also argon's, atomic number. It has that atomic number of 18. So with the noble gas shorthand, what we do is we represent that. And then we write, whatever comes after that noble gas configuration. So we would have argon, right, in terms of, well, what is argon? Well, argon has this configuration of 1s2, 2s2, 2p6, 3s2, 3p6, right? So bromine has all of those shells and electrons, and now here's what we have extra on top of that. And so this is our noble gas shorthand. So that's how we can just, simplify it a little bit in terms of that. Some exceptions. There's definitely more than one exception to electronic configurations, but I just want us to focus in on two of them. Because it gives us a sense of another, state that's kind of heading our way. And so the two that I want us to remember are chromium and copper. So chromium and copper. if we were to look at their electronic configurations, I'm now just going a little bit faster here. For the chromium, right? If you look at chromium, chromium has that, noble gas argon, right? All of these are filled up to argon, and then we end up with going beyond that to then our idea of the 4s and the 3d. So that's what I'm writing here, is with the noble gas shorthand, right? We would have argon, and then we would say 4s2, 4d4. And so what we find is that is incorrect. Right? And this is the idea of an exception. And I apologize with that 4 up top. That should be a 3 there. My bad. But still incorrect. And it's incorrect from this idea of the electrons that we have. There's something special about this particular 3D state. So there's our one exception. If we do copper, we're going to find something very similar is happening with the copper. That our copper would be argon 4s1 3d9, according to what we've been learning in this lecture, or rather 4s2 3d9, according to this lecture. But again, that is incorrect with these electrons as we have them. So for copper, it would be really argon 4s1 3d10. And so that is correct. Again, this is one of these exceptions that we've been talking about. There's more than one, but these are the two that I want us to actually know. So we could ask the question then, what is going on? And so in degenerate orbitals, there are, two electronic configurations. Which are more stable than the others. And, one is when the degenerate orbitals are half full. So we have basically one electron in each degenerate. Or completely full. Where now we have two electrons in each degenerate. So there's this inherent stable state. When you talk about stability, it's where we have degenerate orbitals are half full or completely full. That really helps in understanding. And I don't want us to say that this is something that's always happening all the time, but it does give us some logic in going forward to the periodic trends that we're going to get into later in this lecture. So if we look at those examples again with our chromium, we would have, let's say, our argon, and then we would have our, our D shell. And so we could do this, this way, and this is the incorrect way. And we want to remember this is an exception. I mean, most times it'll be just fine. So you don't want to start applying this all the time. These are just two exceptions that I want us to know. That we end up with just a better state for chromium with this particular electronic configuration. And let's do that maybe a different color here so we can see the differences. And so this is correct. And so it's this idea here with this half full degenerate orbitals is why chromium looks like this. And we can do the same thing with the copper. With our copper, we had the first incorrect one. We'd end up something like this. Again, remember, this is an exception. This isn't how it normally happens. It's just these two that I'm trying to highlight. And what copper really likes or prefers would be now something like we saw with the chromium. Where we have now this set up. And so this is correct. And it's this idea that we have now a completely full degenerate set of orbitals. And that's why, copper looks like this. So that is two exceptions to these rules that we've been talking about as far as the off-ball principle, as well as, Hund's rule, etc. And for the most part, the elements tend to listen to the principle, the off-ball and Hund's that we've talked about. These are just those two exceptions. we look at, electronic configurations for ions, just realize that this is the same for a neutral, or same as for a neutral element, so we've still found the same criterion. Adding of electrons goes to the highest orbital, or goes to the highest energy orbital. You still want to remember Hund's rule, or really both. Off ball for the highest, and Hund's as far as where you're going to put that if you're in a degenerate set. Removing of electrons comes from the highest energy orbital as well. And so we're talking about the difference between, making a cation here in terms of removing electrons, or an anion in terms of gaining electrons. But we still do it, much the same way. So, as an example, we could look at, chlorine, and bring the table back to us here. Here we have our chlorine way off to the right here with that atomic number of 17. All right, so we have 17 electrons to take care of. And we also have that, noble gas configuration idea. So as far as our electronic configuration would go, we would have neon, and then we would have 3s2, 3p5. So that will be chlorine. If we go to chloride, where now we have, this -1 charge, that means we have 18 electrons, and we just add it to that outward shell. So now we go to 3p6. And this just so happens to be the same as argon, for that matter. But because we have the negative charge, right, we have an extra electron now. And so that extra electron gets put into the highest energy orbital. In this case, that last remaining 3p set. Another example, just on the flip side of that, would be maybe looking at sodium. And if we look at sodium, sodium has 18 electrons. We see sodium off to the left now. And it also has that neon gas, core set, and it would be 3s1 in terms of its electronic configuration. Now let's look at sodium plus 1. Well, now that would be actually 10 electrons. And that means that we would have something that looks like this. It is sodium, so we do have that 3s orbital normally there. We're showing with the 0 that we've actually removed, removed that electron. So it is pretty much the same as neon. So that's adding electrons, removing electrons on some elements here in terms of the electronic configuration. There's a bit of a glitch, or I should say, a bit of a problem spot for students when we're talking about removing electrons from, transition metals. And so, as an example of this, we could go back to maybe our copper example to try to reinforce this notion. But first, let's set down the rule system here. Is that when removing electrons from transition metals, you always have this scenario, or you always have this, general configuration where you have N, and then we have our S, and that's going to be full. And then you're going to have, N minus 1 D. Sorry for that. That probably is a little bit confusing there. But that's the notion that you're always going to find a certain setup that's actually going to happen with these particular transition metals. And so let's focus in on that, and I can highlight that little bit there I put at the end. And we can look at that example of copper, where we are right here. So that means we have our noble gas of argon, and then we're going forward with that. And so we find that for copper, we would have this 4s1 3d10 configuration. Again, remember this idea that this is an exception. Okay? But what I'm trying to get at is this idea of an SD relationship. Is that you have this SD relationship just like you have off to the right. And I guess I should get rid of the 2 there, or the squared, and that might make a little bit more sense. Usually that we do see 2 electrons there. Another example, just to get away from the exception, would be maybe vanadium. right? So our copper is that exception. Vanadium, it's not an exception. It's right here. And so with vanadium, we could say that we have, argon as well. 4s2 3d3. Right, so those are the two two examples, but we see the same notion again of this S-D relationship, right? Just like we see in the top right hand corner, where we have this NS, in this case 4S, and then N minus 1D, and then that would be 3. So we have the 3D. So, and that's really always going to be happening in this transition metal block. We see this scenario happen quite often. So you always have that general formula, and that means you must remove electrons from the highest energy orbital. Between these levels, the S orbital is technically higher in energy than the D orbital. And again, this is specific. Specific for transition metals. So if we come back to maybe that last example for the vanadium, where we have argon 4s2 3d3, and just so we have that image of the table, we can bring the table back here. We're looking at vanadium. But when we look at an example of, let's say, vanadium plus 1, and I write the same type of core configuration, but now I have this idea of 4s and 3d, where does the electron get pulled from? It gets pulled from the higher energy orbital. So when we look at these orbitals, n is equal to 4, right, is greater energy than n is equal to 3. And that's going back to that Schrodinger equation that we actually have talked about in the past. So that's why we remove from the 4s in this particular example. So that would be vanadium plus 1. We can continue that example with the copper, right? Because we were looking at copper there earlier too. Copper, again, that exception of 4s1 3d10. When we get into copper plus 1, we find the same, phenomenon occurring. Is that, the transition metal metal loses from the, higher S as opposed to the lower D. Right, and so that's why we're seeing that loss there. This idea has actually been proven with the notion of diamagnetism and paramagnetism. So when we look at this idea, an element can be either diamagnetic or paramagnetic. Diamagnetic means that all your valence electrons are paired. This is something that is like repulsive, or I shouldn't say repulsive, really unaffected by a magnet. And then we have paramagnetic. And that means that there are unpaired electrons in the valence shell. These elements are actually attracted to a magnet. So if we look at, for instance, zinc, zinc is off to the right, and we would say that, much like with this, copper scenario that we've been kind of playing around with here, we would have zinc with its, 30 electrons, and we would simply, hopefully we're getting really good at this now, with that noble gas configuration, we have 4s2 3d10. Right, these are all paired. Right, so since they're all paired, zinc is diamagnetic. If we go to copper, which we've already done, right next door with its 29 electrons. Remember, it's actually the exception. This 4s1 3d10. And so here, now not all electrons are paired. Copper is paramagnetic. And that also describes how we know about this form of copper. In the sense of, if we remove an electron, let's say we have copper plus 1. So now we have one less electron. We should have something that looks like this. And if that was the case, if it was 4s1 3d10 with copper neutral, and now we're losing one electron, we should have something now that's actually diamagnetic. If copper wasn't an exception, and it was like 4s2 3d9, that means both coppers, copper neutral and copper plus 1, would be paramagnetic. But what we do observe is that here, in terms of our copper plus 2, is that all of these electrons are paired. And copper plus 1 is actually diamagnetic. So there's some proof into that concept as far as, there's exceptions and there's experimental proof as to where those exceptions come from. And where a lot of the other exceptions come from as well. Remember, stick to the off-ball principle, stick to Hund's rule, right? And that's what I want you guys and gals to do. The only two ones I want you to be wary of are the copper and the chromium. So keep that in mind.